Bismillah ar-Rahman ar-Rahim. Now we'll do section 4.4. Mainly we're talking about what? Basis and the dimension of the vector space. These are the two things. So what they mean by the basis? A finite set of vectors in a vector space is called the basis for V, provided what? Two things. These vectors linear independent and they span V. It means any vector in V can be written as a linear combination of those vectors. Okay. We have this theorem, which says what? The basis, you can look at it as the maximal linear independent set. It means what? If we have any set, assuming we have a basis of n elements, it means that I have the basis of n elements. It means any set of more than n vectors is linearly dependent, will be linearly dependent, because we look at the basis, the maximal linear independent set. If you add one element to it, then it will not be linear independent anymore. They define the dimension. What's the dimension? Is the number of elements in a basis. Why this is okay? Yeah. By the way, when you have a vector space, you will have different bases, but the number of elements in the basis should be the same. So because of that, we define the dimension. What's the dimension? It's the number of elements in the basis. Because that any two bases should have the same number of vectors. Any two bases, but a vector space, they have the same number of vectors. If the number is finite, then we call it finite dimensional. If not, then they call it infinite dimensional. And we call the dimension like in Rn. What's the dimension of Rn? N. Because the basis has n vectors or n elements. Okay, like this one. This is one of the bases. I know bases, one of the bases, E1, E2, up to En. Okay, why this is true? Let me check the conditions. Easy to check the condition. One, linear independent. Why is linear independent? Because I know that if I find the determinant of this vector, of these n vectors, I have what? This is 1, this is 0, this is 0. So you have, for sure, the determinant is equal to 1. It is not equal to 0. So E1 up to 2n are linear independent. Not only that, any vector, take a vector, x belongs to Rn, means x, I can write it, yeah, x1, x2, up to xn. Then this x can be written as x1 E1 plus x2 E2 plus xn En. Means E1 up to En span Rn. So they form a basis. Why is that? Because they are linear independent. This is the definition. Linear independent and span. So they are linear independent and they span Rn. Any vector in Rn, any vector. Huh? I wrote it in general. Can be written as a linear combination of those n vectors. Actually, we know before, or we'll do it this time. Yeah, we'll do it this time. Okay. Yeah, we'll come back to that. Actually, I don't need to, since there are n vectors in Rn, I know the dimension of Rn is n. I don't need to prove these two. One of them is enough. Usually we do it with the linear independent. Okay. Determine whether the vectors form a basis for R4 or not. You remember in 4.1, I think, or 4.2, 4.1, we said if you have any, if you have an Rn, huh? V equal Rn, any set of n linear independent vectors for a basis. If the vector is Rn, huh? So the dimension of V is n. So any set of n linear independent, if they have the same number, I don't need to prove the linear independent and span. One of them will be enough. And usually we do the linear independent. So enough for me to show that these vectors are linear independent, to show they form a basis. How to show they are linear independent or not? I will find the determinant V1, V2, V3, V4. And that will be 1 minus 1 minus 2 minus 3, 1 minus 1, 2, 3, 1 minus 1 minus 3 minus 2, 0, 3 minus 1, 2. So we do now the operations. 1, 1, 1, 0. What I have? Times 1 and add, that will be 0, 0, 0. 1 and add, that will be 3. Times 2 and add, that will be 0, 2, 4. 2 minus 3, that is minus 1. That is minus 1. Okay. Times 3 and add, that will be 0. Times 3 and add, that will be 6. Times 3 and add, that will be 1. Times 3 and add, that will be 1. Times 3 and add, that will be 2. Now I'll do the expansion with the first column. We'll do the expansion with the first column. Find the determinant. So I have cancelled this with this to get what? Determinant. It's 1 times the determinant of the remaining. 0, 0, 3, 4, minus 1, minus 1, 6, 1, 2. Now I'll do the expansion with the first row. Okay. That give me what? 1 plus minus plus, that's times 3 times the remaining, which I move this and this. That will be 4 minus 1, 6, 1. That give me what? 1 times 3, 4 plus 6. So the answer is 30. The most important, not equal to 0. It means the set V1, V2, V3, V4 is a linear independent set. Linear independent set. And that means they form a basis for R4. They form a basis for R4 since they are in R4. And then the dimension of R4, and they are 4 vectors. Since they are 4 vectors in R4. 4 vectors in R4. This is R4, 1, 2, 3, 4, and we can count them as 4 vectors. Okay, now the question is different now. Find the basis for the indicated subspace. The idea is very simple. What you will do this. You remember in question in 4.2, where we do these free variables and leading variables. Okay, the number of free variables that what will give us the dimension, and that what will give us the basis. Okay, so what is the idea? I can rewrite this. Well, what is the space? The space is V is all x, y, and z, such that x minus 2y plus 5z equal to 0. So how many elements in that space? I have infinitely many elements, because if x is 0 and y is 1, z will be a number. Yeah, so you have different elements, infinitely many elements. Okay, Now I want to rewrite it in an easy way where I can have a basis, or I can write it as a linear combination of some vectors. Okay, so what is the idea? I will make this in terms of free variables and leading variables. So if you rewrite this, x equal 2y minus 5z. So what is the free variables? They are y and z. What I mean by the free variables? These are the variables when I can put any number. This will be the free variables. Leading variable will be x. Someone will ask, can I make the free variables x and y? Yes, you can do this. Up to you. You can do it in different way. Because of that, we have different bases. But the number of elements in the bases should be the same, which is the dimension. Okay. Now, I will use this free variables idea, like what we did before in 4.2, and they will call I have y and z. Using this, I will let y equal t and z equal s, for example. Like it, so it means x will be equal to t minus 5s. Okay, now I will come back to the vector, which is this one. It will be what now? My vector, I can rewrite it. What is x? 2t minus 5s, and I have y is t, and z is s. So if I take t as a common factor, I have 2, 1, 0. If I take s as a common factor, it will be minus 5, 0, 1. Those will be those what will make those what will make the basis. You can check, they are linear independent and very clear. Any vector satisfying this condition can be written as a linear combination of these two vectors. Yeah, because I start with this. I start with this vector with this relation. Make it in that way. So the bases will be V1 and V2. Mainly these two vectors. Is it the only one? No. Because of what? Because I can take the free variables, not y and z. I can take it x and y and make it in terms of z. You can't do this. So you have different bases. But there, the number of elements should be the same. So the dimension equal to. He did not ask about the dimension, but just for curiosity. As I said, the dimension, any two bases, they have the same number of vectors, which is the dimension. Which is we call the dimension. Yeah, this idea of vector space is not only for vectors in R1, R2, R3, or Rn. No, it can be for any collection of elements. So if we talk about polynomials of degree 2. Okay, so this is polynomials of degree 2. What is it? Is p of x, p2 of x equal what? A 2x squared plus a1x plus a0. This is the polynomials of degree 2. It contains of all of these polynomials. Says that a0 are constant. Says that a0, a1, a2 are constant. So I have a collection of infinitely many elements. Okay. Can I think of vectors or elements generate all of these or this subspace? Yes, it's subspace. Why is the vector space? Because if you have any two polynomial of degree 2 and you add it to polynomial of degree 2, it will be still polynomial of degree 2. You multiply by a number, you are still polynomial of degree 2. Polynomial of degree at most 2. Huh? Yeah, this is what they mean. And these constants can be 0. Okay, so Now, the bases, one of the bases, which is, it can be easily seen. As we said before, we don't have only one set of bases. We have different bases, huh? But this is one set, very clear, 1x, x squared. This set of elements make a basis. Why? Because if they are linear independent, yeah, how to prove they're linear independent? We need, I think, chapter 5. Yeah, but take it from me, they are linear independent. Okay, 2, they span P2. They span P2. Why? Because take any x, any element, call it what? V in P2. Then V is what? Will be written a2x squared plus a1x plus a0. This is the way to be written, which is, can be written as a2. Call this the basis, v1 equal 1, v2 equal x, v3 equal x squared. So it can be written as a2 v3 plus a1 v2 plus a0 v1. It means any vector in B2 can be written as a linear combination of those three. So they span B2. So this is a basis for P2. What's the dimension? It's not 2. The dimension is 3. Count them. 1, 2, 3. Dimension is 3. So for P2, dimension is 3 because I have 1x x squared. Huh? I have the constant. Okay. Now this is the set of all polynomials, not with a fixed degree. It can be extended. So the basis will be what? 1x x squared, x to the power n, etc. So I have how many elements? We have infinitely many elements. So they call it infinite dimensional space, vector space. Okay. Now, just the dimension of Rn, just to review what we did. Dimension of Rn, n. This is, I mean, something default. Dimension of 0, they call it 0 because there is no base. Set of all polynomials, this is infinite dimension. Infinite dimension. Because you don't have, it's not for a fixed n. This is for a fixed n. This is for a fixed n. So I can take bases 1x x squared up to xn. What is the dimension? It's not n, it's n plus 1. The dimension is n plus 1 because I have n plus 1 elements. Okay. Yeah, this theorem is a very nice theorem. We need to understand it. If you have a vector space and the dimension of V is equal to n, I have a subset of V. Okay. Think about it this way. If S is linearly independent and consists of n vectors, let me take 1 and 3, this and this. These two. Only these two. It says what? If we have a vector where the dimension is n, so the number of elements for the basis is n, and you have a subset consists of n vectors, there's no need to prove linear independent and span to show this set is a basis. One of them will be enough, and that's what we did in this example. In this example, to show this subset, the subset, they call it W, for example. here V1, V2, V3, V4. How many vectors we have? We have 4 vectors. The dimension is 4. We know the dimension of R4 is 4. So to show this set form a basis, I don't need to show both of them, linear independent and span. One of them will be enough. And usually we do the linear independence. It's easy to do through this determinant. That's the meaning of 1 and 3. Okay. The other ones, now let me deal with the, let me try summarize 2 and 4 also with 1 and 3. Let me try to put it here. Okay, I have the dimension B is equal to N. So assume I have the S consists of V1, V2 up to Vk. Okay, I put a different number. So the subset contains of K vectors. Okay, so I have these 3 cases. Case 1, K less than N. The number of elements in the subset less than the number of elements in the basis, which is the dimension. So I have this case. If S has less than N vectors, then it cannot span V. Then S cannot span V. And that means what? S cannot form a basis. This is case 1. Case 2. K is greater than N. It says if S has more than N vector, then S linear dependent. Right away, S is linear dependent. That means S cannot form a basis. Case 3. K is equal to N. 2 and 4, they said what? I don't need to check both linear independent and span. One of them is enough to check. So check either linear independent or span. Proof that S form a basis. So if I have the dimension is N and I have the number of vectors less than N or greater than N, for sure this set cannot form a basis. If it is equal to N, I need to check, especially checking linear independent. How to check linear independent? Through the determinant. Since the same, I have the same number. Okay, so let me apply this. Yeah, these. Well, before I apply this, let me. These two means what? It's like the basis will will contain the linear independent subset, because we said the basis is the maximal linear independent subset. And if S is span V, then S contains the basis. So like the basis is in the middle between linear independent group and the span group. Okay. Now, let me do this one, which is concerning these things, or concerning these cases. 1A. How many vectors I have? Oh, we are in what? We are in R3. So what's the dimension here? Dimension of R3, I know it's 3. Okay, how many vectors do we have? 1, 2, 3, 4. I have 4 vectors in R3. Which case? The set S is what? U1, U2, U3, U4. So it goes 4 vectors. I am in this case. K is greater than N. the number of vectors of the subset S, which I call it V1, V2 up to Vk, is more than. So right away, this cannot form a basis. Cannot form a basis. Because they are linear dependent. Let me do C, then we'll go back to B. How many vectors we have? We have 2 vectors in R3. So right away, this is my S. Cannot form a basis. Cannot form a basis. Okay. Case B. Yeah. Now I have 3 vectors in R3. So what is my S? It is U1, U2, U3. I need to be careful here. I cannot conclude. I am in this case. In number C, I have this case. So this is C case. This is A case. This is B case. So I need to check this set. I have 3 vectors. 1, 2, 3. This set is linear independent or not. This is enough for me. So it means I need to do the determinant. I need to do the determinant. Okay, let me do the determinant. Let me space here. Okay, underline the vectors. I have U1, 1, 7 minus 3. This is U1. What is U2? U2, 2, 1, 4. U3, 1, U8. 6, 5. 6, 5. So check determinant V1, V2, V3. Which is this determinant? 1, 7 minus 3. 1, 7 minus 3. 2, 1, 4. 6, 5, 1. I'll do this trick to have more zeros. I have 1, 2, 6. Multiply by minus 7 and add, that will be 0. By minus 7 and add, that will be minus 13. Minus 7 and add, wow, what is this? Minus 42 plus 5, which is minus 37. Yes. Now multiply by 3 and add, that will be 0. By 3 and add, 2 times 3 is 6, 10. By 3 and add, 19. Okay. So now I'll do the expansion. I'll cancel this with this. So have this determinant, which is minus 13 times 19 plus 370. Impossible that to be 370 because the unit digit is not 0. So this is not equal to 0. This is the most important, not equal to 0. It means this set is a linear independent set. So they form a basis. I think these 3 examples is very nice. We have the 3 cases, huh? We have the 3 cases. Case A, where the number of vectors, the number of vectors is more than, and case C, where the number of vectors is less. Case B, where the number of vectors is the same as the dimension of the vector of the space. Okay. You remember what we did in section 4.2, example 5, I think, last example. I don't remember. I think example 5. Last example in section 4.2, where I have solution space. We're talking about what? We have solution space with the homogeneous system. We have homogeneous system, Ax equals 0. For a fixed matrix, the matrix A is fixed. Okay. So now, where A is M by N, huh? A is M by N matrix. Okay. So we have a collection of elements. We have many values of x, infinitely many values of x. Satisfying this. So now I need to find the basis, and we agree. By the way, this is a solution space which has all x, so that ax equals 0. This is a solution space. This is a space. We call it the solution space of the homogeneous system. We need to find bases for that. Find bases for the value. What we did in 4.2, in the last example in 4.2, is the same idea. What I will do, first, I will reduce the coefficient matrix A to echelon form. I'll do the leading variables and the free variables. The leading variables and the free variables. The free variables, you can give them parameters and then solve for the leading variables. Then you can make the vectors. He's doing it here in by setting these elements. Take one to be 1 and the rest 0 to find the vector, or you can take it by take a common factor, which this is the way we'll do it. Note the dimension of the solution space of this solution space. The dimension is the number of free variables. So if you ask me about the dimension of this solution space of a homogeneous system, no need to do all of this. When I reach free variables, just make it echelon form. I have the free variables. The number of free variables will be the dimension right away. Okay, let me do this example. Find the solution space for the following system. Also find the basis and then find the dimension. Okay, so what is the solution space? What is A? A will be 1 minus 4, 1 minus 4, 1, 1, 2, 1, 1, 1, 8, 6. So the space will be all x, so that ax equals 0. That will be my space. How to find the basis? I follow the rule. First, I need to reduce the matrix into echelon form. Okay, let us work on the matrix. That will be 1, 1, 1, minus 4, 2, 1, 1, 1, 1, minus 4, 8, 6. I have it with 0, 0, 0. And no need for this, because everything times 0, add to 0 will not do any change. But yeah, for completeness, let me do it like this. I need to take this is make it 0. How? Multiply the first row by minus 1 and add the second row, and the same thing with the third row. I'm doing these operations, elementary row operations. Minus 1 and add, that will be 0. Minus 1 and add, that will be 6. Minus 1 and add, that will be 0. Minus 1 and add, that will be 12. That will be 0. Minus 1 and add, that will be 0. Minus 1 and add, that will be 5. That will be 0. Minus 1 and add, that will be 10. Okay. So now I can take this is 1 by divide by 1 over 6, R2, and 1 over 5, R3. What will be the new matrix? 1 minus 4 minus 1 minus 4. This is 0. This is 0, 1, 0, 2, 0, 0, 1, 0, 2, 0. Okay. Now what I have? I can multiply the second row by minus 1 and add it to the third row to get this. So to make it in the echelon form. 0, 1, 0, 2, 0, 0, 0, 0, 0, 0. That's it. Now this is echelon form. So it's already in the echelon form. Echelon form. What he said, this is my first step. To identify the leading variables and the free variables. Okay. What are the leading variables? I need this and this. By the way, this is for x1, this is for x2, this is for x3, this is for x4. So leading variables will be x1, x2. Free variables, x3, x4. As I said before, someone, he said, no, I don't want the leading variables x1, x2. I want it to be x3, x4. You can't do this. But now, this is just a procedure. Okay. So, but you will get different bases, which is okay. But the dimension should be the same. Okay, then now I rewrite these two equations. So I have x1 minus 4x2 minus x3 minus 4x4 equals 0. And I have x2 plus 2x4 equals 0. Here, when I have three variables, that, oops, use this trick. He said, what, use T1, T2? I can use T1, T2. Let x3 equal T1 and x4 equal T2. By the way, what is the dimension? خلاص, the dimension I get it from here. Dimension will be 2. Dimension will be 2, which is the number of three variables. Huh? Okay, so let me call this 1 and 2. From 2, x2 is minus 2x4, which is minus 2 T2. Okay. This is 2. From 1, x1 will be what? 4x2 plus x3 plus 4x4. And that is 4x2, which is minus 8t2. x3 is t1 plus 4t2. That gives me what? t1 minus 4t2. Okay. So now my vector solution. Let me go back to that one. So the x, which is x1, x2, x3, x4. That will be what? Now I plug the numbers. x1 will be this. T1 minus 4t2. x2 minus 2t2. x3 t1. x4 t2. Now I take t1 common factor. What I will have? 1, 0, 1, 0. Take t2 common factor. What you will have? Minus 4, minus 2, 0, 1. I have, this is V1, and this is V2. So the bases will be what? V1, V2. V1, V2, which is 1, 0, 1, 0, and I have minus 4, minus 2, 0, 1. This is the basis. Dimension is equal to 2. How many vectors we have? 2. And as I said, dimension right away, I can get it from the free variable, the number of free variables. No need to go, no need to do the rest of the calculation. If I need to find the dimension, but the basis, I need to do the calculation. Okay. Now find the basis for the following subspace. I'll do the same idea, almost the same idea. How? Why is the same idea? Because if you notice, this is what I have: A plus B equals C plus D, which means A equal minus B plus C plus D. So I have an equation. I can do the same idea, the same trick. What is the free variables? What are the free variables? And what is the leading variable? In this case, the free variables B, C, D. I can put any value, B, C, D. And what is the leading variable? A. You can make it in terms of You can make the leading variable B. Yes. You can make it C. Yes. You can make it D. Yes. It's up to you. It has to, do it the way you like. Okay. But usually we do it this way. Now, you can do it the same way. You can write the three variables. You can give them like variables like T1, T2, T3, something like this. Or you can do it right away. And I can do it. I can say let B equal T1, C equal T2, D equal T3. Or I can write it right away. It's okay. And then I will try to write A in terms of these T1, T2, T3. And very clear, A will be what? Minus T1, because it's minus B, plus T2, plus T3. So the vector X, who A, B, C, D, I wrote it instead of this way, it's okay, the same idea. That will be what? It will be minus T1, plus T2, plus T3, and I have T1, T2, T3. Now, I can take T1 as a common factor. I have what? Minus 1, 1, 0, 0. Can take T2 common factor. Yeah. I have three vectors, huh? Look, this one give me what? The dimension here, from here, without do any more calculation, is equal to 3. With the number of the free variable, then will become 3. That's it. Dimension equal to 3. Okay, now let me try to find the basis. Take T1, have minus 1, 1, 0, 0. I did not do it because of the space, huh? T2, 1, 0, 1, 0, 2, 3. What is it? 1, 0, 0, 1. So these three vectors, this is V1, this is V2, this is V3. V3, sorry. So the basis will be what? V1, V2, V3. Which is minus 1, 1, 0, 0, and 1, 0, 1, 0, and 1, 0, 0, 1. What the dimension of this vector space will be 3. Find the basis of the following subspace. It has two equations. Okay. So it's like I'm solving two system of two equations. A equal B, C equal D plus E. The most important, how many free variables I have. The most important, how many free variables I have. Look at it this way. How many elements of this A, B, C, D, E? I can write it, I can put it freely. I can put any value. So very clear. A, what are the leading variable? Maybe the leading variable will make it. I start with it. A and C. And the free variables will be the rest. B, D, and E. I can put any value B, any value D, any value E. So these are the free variables and the leading variables. As I said before, you can make this T1, T2, T3, or you can do it right away. I can say A, B, C, D, E equal to 1. This is my vector. So I want to write everything in terms of these three free variables. So I need to write A and C in terms of the free variables. The rest I will leave it as is. A equal B, so that it will be B, B. B, I did not change it because it's a free variable. Just I need to change the leading variables. This is D plus E. This is D, this is E. So now I take B as a common factor. What you will have? 1, 1, 0, 0, 0. If we take D as a common factor, what you will have? 0, 0, 1, 1, 0. If we take E common factor, what you will have? 0, 0, 1, 0, 1. So what are the bases? Base consists of what? This is V1, this is V2, this is base 3. Or you can do it, make B T1, D equal T2 equal, you can do it this way or that way. So what is the basis? Would be V1, V2, V3. This is one form of basis. I mean, as I said, you can have different bases by just changing the free variables. Okay, that will be what? 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 1. Not only changing the bases, also on any multiple, huh? Yeah, any multiple also will give me different bases. So what is the dimension? The number of the vectors 3, which is the number of free variables. From here, I can get right away the dimension. No need to do more, I mean, other calculation. Dimension will be 3. These are now the old exams questions. These are the old exam questions. Now I just try to explain the idea. I think I will stop here. As I said, usually I don't like to have long video. So let me stop the recording.